Hello guys, so today we are going to understand the sum of subarray minimums, right? So this is lead code questions and this is very good questions, okay? So I think this question has been asked by the Google and some of my friends recommended me to work on this. Actually, I have skipped these questions on the one of the day in the today question section. I thought this question is a little easy and yeah, but some people have find difficulties. Okay, so let's understand today. So what the sum of subarray minimums? So here you can see that given an array of integer, we find the sum of mean b, where b ranges over very continuous subarray. Okay, since the answer may be large, return minimum modulo 10 to the power 9 plus 7. So we have example first and we will understand what it is saying. So this is the array and it has been given, right? 3 1 2 4. Then we have to find the mean of b. Mean of b means what? Sorry. Mean of b means what? Mean of b means b we have to find which is the mean of the range over the continuous subarray of array. Means if we have this array, correct, we have this array, what will be the subarray? So you can see the subarray. The first element is 3, so we will make 1 3, then 1, then 2, and the last element we have in the array 4. Then we will make the combination what? 3 1 2 1 2 4, and the third combination will be, right, how? 3 1 2 1 2 4 and 3 1 2 4. So total combination, if you will see, we have 3 3 and total 4, means 6 and 4 10. To 10 combinations we have, in which we will find the minimum, right? So this 4, this 4 have minimum value what? It's itself, right? So the same 4 value will come out, but from this 3 combination, 3 and 1, it will come 1, then 1, then 2, and the last one is 1, right? From here, right? So here it will come what? 3 and 1, it will come 1, then here will come 2, then here will come 2, then it will come 3, sorry 1, here it will come 1, and here it will come 1, correct? So all the minimum will come from its subarray, and after this we will add. Means first only 2 steps you have to do. First you have to count, you have to get all the subarray, and then like this, and then you have to do minimum of what? This number. Okay, you have to find the minimum, you have to find the subarray, then you have to find the minimum, and then you have to add. So only 3 steps you have to follow. See, the first step is to consider all the subarray of given array. Then we will do, for each of the subarray we will calculate what? Minimum. And then third, we will add all the minimum calculated from step 2, correct? So in this way we will have the summation of what will we have? We will have the summation of minimum and what we need to return an answer. This is the answer. Okay, so there is the first approach to introduce the concept of what? The first step is the concept of each array element contribution to the answer, correct? Then it uses a monotonic stack, which is very important to arrive this solution. So the second approach applies dynamic programming and build a top of earlier monotonic stack method. So we will understand this one. So two solutions we have. The first one, we will go with the each array element contribution, and second we will go with the monotonic, that will have the DP concept. Okay, so you can see that the first approach is saying monotonic, in which we have the contribution of each element, and we will understand how it is saying that. When thinking about a solution, it often helps to consider the most native approach. It helps cement the understanding of problem. Then we observe area where optimization is possible. So let's do exactly what the question asks us to do. Consider all the possible ranges in the given array, and let's say there are 5 elements in the given array, which is 0 indexed. We can think sub array starting from the 0th element, then the sub array begin at first element, second element, up till the last element, correct? Because array start from what, 0 index to n minus 1, whatever the size we have n, till it will go. We should be able to do this using two nested loop, correct? We have to, because if we want to compare uh, the elements in the array, then you have to only do if 1 2 3 4 5 we have, right? If I want to compare this and this, correct? So there should be a loop in the two loop that will take this value, and there should be uh, another loop that will compare this loop, and this comparison should go continuously. There should be a nested loop, right? So it is saying two nested loops should be there, one responsible for the start point of the range, correct? That is it is saying, and other is for the end of the range. While considering each sub array of range, we calculate the minimum of this range, right? So once we have the minimum range, right, what we will do, we will add this to the running total minimum, and at the end we will return the total as answer. So you can see here we have an example in which what we have 5 7 3 2 1, 5, in which the starting point I and j, the first loop and the nested loop, both have at index what, 5, index 0. This is index 0, 1 2 3 4, correct? 0 to 4. So the first index we have at 5, right? So you can consider like this. We have only one element here, and the minimum will be what? The same we have minimum, current minimum. The current will be the minimum because start and end both at 5. But in this case, when you will see, start it at what, 0, or end is at what, 1, correct? So if we will consider this one, so in the 5 and 7, the current minimum is what? Current minimum is 5 only, correct? So the total running will be what? Now the total running is 5 plus 5, it will be 10. But initially you can see what we have, only 5, that is coming from here, correct? That we have in the current minimum. So total was 0 plus current minimum was what? 5, right? And this was 0, and this is the case we have. Okay, similarly now the start is at what, start is at 5 only, and it will move to what, 3, correct? 1 minute. So the minimum is what, 3 only, right? Similarly it will come to 2, so the minimum is 2, and we will add here, the running is 13, now is the running is what, 15. Okay, next what we have, start is at 0 index, and the last index we have at our last index we have 5. So the current will be what, in 2 and 5, it will be what, the 2, right? And if we will consider this one, uh, current minimum, now the start is will move from what, 0 index to 1 index, and so the end is what? Now indeed will not, end can't be start from here, and will also start from what? The index 1 only, not from the 0. Now the current minimum is 4. In this fashion, what you will do, you will calculate the current minimum and you will add into the running total, and like this we will calculate current minimum and running total. So finally we will have what? The answer 47, because of the two nested loop has been completed, right? So while this solution work, most of the time is spent generating all subarray, right? What we have seen, when we are working for this solution, we are spending all the time on generating subarray, and after that only we are finding the minimum and then uh, adding, correct? Two nested loops, it's, I'll need o n square time, and we can improve further. Can we improve further? Yes, we should. The improving or the brute force, what we will do, you might have noticed that we have been focusing on the range first, right? Once we have a range, we will look to the minimum element in the range. Generating this range is the most consuming part of the algorithm. So at time when trying to optimize a solution, it helps to look at a problem from a new perspective. Indeed, it is possible if we flip the way of approaching this problem. In in the beginning, in the beginning, let's focus on each element instead of focusing on the range. Correct? Then we will figure out the range which it is minimum. By doing this, we are trying to determine each element contribution during the summation of all minimum, right? In minimums. In fact, let it go one step further. Assume that we know the range in which each element is the smallest. If we know that an element is the smallest in the given range, we can determine number of subarray in the range that contain this element, because the element is the smallest in the range. So it will also be the smallest element in the subarray, correct? If the element is small in the nest, right, range, means it will be the smallest in the subarray. Count subarrays, right? Count subarrays and multiply by element will give us the element contribution to the final summation. Is it correct? The count of subarrays multiplied by the element gives us the contribution of the final summation. So let's figure out how to get the number of subarray that contain a specific range. So if we are given an array of integer that will start from 0, 3, 4, 5, 2, 3, 2, 4, 1, like this, we need to find a number of subarrays where 2 is the smallest, correct? 2 is the smallest integer. We can see that 2 is the smallest integer in the range of 1 to 6, denoted that the subarray 3, 4, 5, 2, 3, 4. So all subarray that contains this all the subarray of this range contain 2 will have 2 as a smallest integer. As a result, the question has been reduced to the given range. Find the count of subarray which contains 2. So each subarray is continuous element that contains 2 from the given range. So to count them, we count every subarray before starting 2. Before 2 you can say, right? And 2 ends after 2 at 2. So as explained in this diagram, this is easy way to counting them. So if we will go to understand this one, so we have from 1 to 6, right? To 1 to 6, what we have? We have here element, right? give me a minute. We have 2 here, and it started from uh, start before, right? So these are the element before 2, and these are the element after 2. So the range 2 is the smallest number in the given array, right? So if we will break the range 1 to 6 from here to what? Here, right? 6. Sorry. 1 to 6, correct? So if we will break this, the range before 2, 2 and after 2. This part, and this part, correct? So the what will we have? Left boundary is this, right boundary is this, and this is the center minimum. This is the minimum. Now what we have? Left boundary we have, right boundary we have, and we will make the combinations and we will try to find it out. So if we will count 1 from 3, 4, 5, 3 to 4, this is the one combinations we have in which 2 is there, right? Count 1. Now in the count 2, what we have? We have 3, 4, 5 and 2, and we will take another element, right? What? 3. Only one element. Oh, sorry. The battery was discharged, so I came out. Okay. So now what we have? We have count 2 uh, in which we have 3 as a single count. This time we do not have 3 and 4, only 3 is there in the last. And in this case we don't have the right part, only we have a left boundary and the minimum, correct? You see here the left boundary we have and the 2 we have, and this part is not here now, right? Now if we will go with the combination that contains not from 1, it will have 2 and 3 index, then the fourth index and 5, 6, right? So we are losing one index, that is of 3, correct? Here it was 3, so we are losing that, as you can see here also, right? Now this was a count 4, right? And you can see in here this is the condition, we are taking this and this. Previously we were taking this part and this part, correct? And this part and this part we have taken. Now as you can see here, we have the left boundary, this element, but in the right down we are not taking this line, we are taking this line. Okay, now this was the count 5. Now if we will go with the 4, 5 and 2, right, this is the combination will be this, and in the last we don't have anything. Okay, so 4, 5 and 2 we have. Similarly in the from the left boundary we will take only one, and we will keep all these 3, 4 combinations. Now this was the count 7. If we will consider this one, we'll take one from the left, another from right, correct, this combination, and the last we will take in which we have 5 and 2, and finally we will take only right boundaries, and now 2 we have only one boundaries, and the last it is alone, correct? So total count is what? 12 count we have, and so that there are 12 sub arrays which contains 2, correct? So in this fashion what will happen? The 12 sub array which contains 2, the index of the left minimum, that is called left boundary, and the right boundary is the minimum of index, correct? Right boundary. So there are 12 sub arrays which contains 2, which was the count was this count 4 and count 3, in which what we have 40 into 40 and 7 minus 4, 4 minus 0 and 7 minus 4. So there is 4 into 7, you can say. So total how many count we have? 12 count we have, correct? You understood or not? You see what we have did? 4 minus 0, right? 4 minus 0 and then 7 minus what? 4, correct? The index of, sorry, here, come here, index is 4, this one, so 4 minus what? This 0, and 7 minus this 4, so total is what? This is 4, and this is what? 3, and 4 into 3 what? 12, correct? So this is saying the same answer. Now, as explained above, we can get the total count by multiplying two numbers, right? And the count of the element before 2 including 2, and count of the element after 2. There are 4 elements uh, before ending 2, that is 3 4 5 2, and 3 elements after that, that is 2 3 2 3 4. So the total count is what? 3 into 4, that we have got 12. So as we know that the count of the subarray where each element is the smallest, and we can deduce the amount each element will contribute the final summation, correct? So for any element it will be the element into the count of the subarray where it is smallest. So we can assume this amount for every element to get the answer, right? So now only remaining part of the puzzle is how to get the range in which element is smallest. For this, we find nearest element on the left which is less than itself. Then find the closest on the right which is less than itself. So there is if condition I and j are the indices of the element on the left and right. So I plus 1 and j minus 1, which create our range. So we can use a minimum monotonic increasing stack to determine the value of I and j. Monotonic stacks are used to calculate the previous smaller element and the next smaller element in near time complexity. So please note that at this point the problem is very similar to the given problem, right? 84, the large rectangle in histogram. So except the summation part, this is almost similar part. So further, if you want these ones, you can comment in the comment box. I'll share this program. Now it is saying that finding the previous smallest and next smallest element with a monotonic stack. So let's first understand this monotonic increasing array or a stack. An array is the called monotonically increasing if two indices I and j, where I is greater than j and array of I is greater than equal to j, always holds true if the array is strictly increasing. The relation can be changed to greater than in the place of greater than equal to. Other words, what we will do, every element is greater than or equal to is if the array is not strictly increasing. The the last element for a monotonically decreasing array or stack, the opposite will hold. But here, because we are interested in next and previous smallest element, we only care about a monotonic increasing stack. Note, if we want to know the next and the previous large element, we can use monotonically decreasing stack because we are interested in the next and previous smallest element. We don't need to monotonically decreasing. So how build a monotonically increasing stack? To build monotonically increasing stack, as we iterate through an array element, we push them onto the stack. But before pushing an element, we ensure that always increasing. To build increasing stack, what we can do? Right? Sorry. Increasing a stack, what we can do? We can iterate through an array. We will push them onto the stack. But before pushing an element, we ensure the always increasing property is maintained. It means if the item at the top of the stack is bigger than or equal to the current item under iteration, we first pop it off before pushing the current element on the top. So but how we can how we can building a monotonically increasing stack we are helpful, right? So we'll see the moment, don't worry. The answer lies in the process of building it. Right? Okay. So as a new item get added on the stack, older items are removed from the top if they are bigger. In other words, the item are getting popped must be greater than or equal to the incoming element. We can also say the incoming element must be the next smallest element of the item going off the stack. So every time an item is popped, we get to know about its next element, smallest element. If the stack is not empty, the stack pop would contain the previous item. That because whenever a new item is added to the stack, we ensure all the bigger items are removed first. So the stack guarantee that previous element has to be previous element. If the stack became empty, all at the time of remove the element, it indicates that the outgoing item is the smallest item seen so far. So also note that once the process is complete, the stack contains a series of items sorted in the increasing order. So these are also the items that have no smallest item after themselves, and their previous smaller items are stored right before them in the stack. So let's see all the process with the help of element, and we'll see this as example. So we have given in the example, right, uh, 0 to 6 index we have, in which 8, 6, 3, and these are the element we have. So if initially the stack is empty, right, will be empty. So if 8 is pushed into the stack, what will happen? The element will come here, correct, in the stack. Now we will see 6 is a small next element we have 6 we have, and which is a smaller than what, 8. So 8 is removed from the stack, right, and it will we already we have, right. So we have to, what we have to do, we have to remove it, and now because 6 is the smallest element, correct, 6 is smaller than 8, so 8 is removed from the stack, correct. Now what you can see that next smallest element is for 8, 8 is 6, correct. Now we have to move, so because the stack is empty, previous smaller doesn't exist, or we can say it is -1, correct. Now 6 is pushed into the stack, right, and now the next element we have 3 is the smallest than 6, so 6 is removed from the stack, and what we will do, we will check, right, the similar way. So when the next element will come, right, the 5 is bigger than 3, right, so what will happen, we will push into the stack now, this in the similar fashion we will do, and this process we have to go on till the uh, last index, correct. So now the final element what we have 2, and the smallest is 9, so 9 has to be removed, and the current index will be what we have 3, 4, and the next we will have what, 2, right. So we will make it what, 2 is the smallest element from 4, then we will remove the 4 from the stack, and we will maintain the stack in the final, correct, like this you can see. So because the stack is empty, there is no previous element 2, and the finally stack will be empty, and there is no next smaller to 2. So the question is, the approach is edge case duplicate elements, right. So let's understand directly here. So if the stack is empty, right, initially 3 is pushed into the stack because the index 0 have 3 element, and here what we have, stack next value we have 4, so 4 is bigger than 3, so it is satisfy the stack property, and so 4 is pushed into the stack. Next, what we have, 4 greater than equal to 4, the same duplicate value we have. In this case, we will remove, what we will do, we will check if the array of mid into next smallest element minus mid into mid minus previous element, right? Like this you can do, or mid the index of the element remove from the stack. Now what we have, 3 4 we have, next element we got what, 4, means that is a duplicate element, right? So we will remove from the stack because it is greater than equal to 4. Now mid is what, 1, next smallest is 2, and previous smallest is what, 0, from the stack top, right? The contribution is what, 4 into 2 minus 1 into 1 minus 0, based on the formula, right? Now total what we have, 4 we have, we will take mid as a 1, and smallest is what, 2, previous smallest is what, 0, and the total contribution is what, 4. Now 4 is the bigger element than 3, so it is added to the stack, and 5 is the bigger than 4, so it is added to the stack. Now 4, it will come 4 again, and then we will check 5 is greater than equal to 4, so the stack top is removed, correct? The top element will get removed. Now we have mid equal to 3, next element what we have, 4, previous is 2. Now the contribution will happen 5 into 4 minus 3 into 3 minus 2, and then total is 4 plus 5 plus 4 plus 5 equal to 9. Mid is 3, next element is 4, and previous one is 2, like this. So we will check greater than equal to, we will remove the duplicate element. In this way we will continue, and at the end what we will get, we will get all the total, mid, next, previous, and these things. So finally we will have 62 as a value, and the previous element we don't have now, right? As a minus 1 we have, so we will calculate like this. So the implementation is what, how we have mod, then we have the stack, right? We'll take sum of minimum, we will take 0, we will take 2 loop right here, one for the building the monotonically increasing in the stack, and we will check the condition, right? It will start from 0 to array length, and then in which we will take a stack, right? So we will take a stack dot empty. If not, if this is not empty, and I equal to array dot length, or array peak value we have greater than equal to I. In that case what we will do, we will calculate the mid, then we will check left boundary and the right boundary, and then we will count using this formula, and then we will what we will do, we will calculate the sum of minimums, and then we will take mod, right? And then we will push the stack, and at the last what we will do, we will return this sum of minimums. So the time complexity will remain O of n, and space will be remain same O n. Another approach we have monotonic stack, and then we will see using the dynamic programming in the part 2.